Hello everyone and welcome to another video. So today I would like to spend a little bit of time talking about going from a transfer function representation to a state space representation. So this is actually a direct continuation of our previous video where we actually looked at going in the opposite direction. So in other words, in our previous video what we talked about was if you had a state space representation, how did you transform that into a transfer function representation of a dynamic system? So today what I would like to do is think about going the other direction. So now I would like to say, what happens if we start from a transfer function representation and we would like to turn this into a state space realization or a state space representation? So that's the direction that we're headed today. So again, if you haven't watched our previous video where we went from state space to transfer function, I would recommend you go ahead, take a moment, pause, watch that video first, because we're going to build off some of those ideas, as well as that previous video kind of helped set the stage of some of the techniques that we're going to be applying and using, and just kind of get you in the right mindset of how to think about these two different representations. So if you've already done this and it sounds good to you to jump into going from transfer function to state space, let's go ahead, let me erase the board and we'll go ahead and get started. All right, so let's just consider a general transfer function as shown up here, right? It's nothing more than an nth order polynomial on top of an nth order polynomial, okay? And again, in most times with control theory, what we're interested in looking at is proper transfer functions where the order of the denominator is greater than or equal than the order of the numerator. Now, for the rest of the discussion today, what I want to consider is strictly proper transfer functions. That's where the denominator is strictly greater than the order of the numerator. Okay, so there's going to be a minor tweak on what we're discussing today if you want to apply this to proper systems where the order of the top and bottom are the same, but we'll leave that as an exercise to the viewer. Okay, so I always like to look at concrete examples. So let's consider the case of where you have 3 poles and 2 zeros. Okay, so your transfer function is going to look something like this, right? A second order polynomial on top of a third order polynomial. Okay, now what I'd like to do right now is, you know what, we could rewrite this transfer function if we wanted to, all right? So what we could do is let's break this up into 3 different components. Let's write this as maybe b2s squared all over the denominator, right? S cubed plus a2s squared plus a1s plus a0, right? This plus, now let's do this next one, b1s all over basically the same thing, right? Plus b0 all over the same denominator, right? So you could break this up like this if you want, right? We could even take this one step further if you want, and let's just write the this numerator outside. So what I mean by this is basically let's write this thing like b2s squared, excuse me, times 1 over, I'm going to write this thing as the denominator. It's just this thing right here, right? You could do this plus b1s times 1 over the denominator, right? Plus b0 times 1 over the denominator, right? Would everyone agree that's the exact same thing? Right? So actually, you know what? Let's call this term 1 over the denominator. Maybe let's call this thing, I don't know, let's call it G critical or G core or something like that. That's 1 all over, I'll write it out here. So, right, it's s cubed plus a2s squared plus a1s plus a0, right? Okay. Okay, so then what we could do is, again, I guess you could rewrite this whole thing, right? Here's the original transfer function, right, which was the ratio of the entire output over the input, right? This is now going to look something like b2s squared times gc of s, right? Plus b1s times gc of s plus b0 times gc of s, right? We haven't done anything, we've just basically rewritten this in a slightly different format, right? Now, what's interesting is if I want to calculate the output, right, I just need to multiply this entire side by the input, right? So in other words, the output of the system, y of s, it's nothing more than, let's write it like this, b2s squared times gc of s times u of s, plus b1s gc of s times u of s plus b0 gc of s times u of s. Right? Would everyone agree? Okay, so now if you want to, we could visualize this as sort of a block diagram representation, right? So the entire output is the sum of this plus this plus this, right? And if you look at these three terms, let's start over here. This is maybe the easiest one to visualize, right? So I like to think about this as, okay, you've got U coming in, right? And then what we're going to do is we're going to run it through GC. Right, so here's GC, right? And then all you have to do is what? Multiply this by B0, right? So something like this, B0, right? That's this term right here. That's this signal, okay? And then obviously we're gonna have to add these things together, so I'm gonna have a plus, 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 okay? Now let's take care of this term, right? So again, you see, here's the GCU and the B1, so I can basically do this. I could say GC of S, and then what we could do is I could write this, tell you what, let's actually take into account this S here, right? This is an S, right? And then hit it with the B1, right? And that gets added. This goes like this, right? And then finally, let's do this, the bottom one, right? GC of S. And now I've got two S's right here, right? There's an S squared, so there's an S here, and then an S here, and then we hit it with the B2, right? Okay? And now this is the total component Y, right? Would everyone agree, right? Okay, so what's interesting about this now is let's go ahead and take a look at maybe like this signal right here, right? The thing that's coming out of this GC transfer function that we made up top, right? So I don't know, let's call this maybe YC, right? All of these signals here are YC, right? Okay. So if I look at this YC, maybe let me come over here. Tell you what, give me a second to erase this board and we'll pick this up. All right, I erased this side of the board and added some lines here so you don't have to watch me write this all out. So again, look, we are interested in that signal YC, right? This signal right here, and you can clearly see that YC is just a transfer function GC times U, right? So that's what we've written here, okay? Then what is GC? Well, I'm just going to substitute our expression for GC in here, okay? Now, all I'm going to do is I'm going to move this denominator to the other side, so we end up with YC times the denominator is equal to U, right? Now, let's distribute the Y through all of these terms. That's what you end up with right here, okay? And now, let's pick it up from this point. Now, at this point, what we may want to do is let's just go ahead and take the inverse Laplace transform of this right here, of both sides. And again, if you need a little bit of a refresher on the Laplace transform or the inverse Laplace transform, right? Please check out these two videos where we discuss this in excruciating detail, right? So let me take the inverse Laplace transform of both sides, all right? And I guess I'm gonna have to move this over here. So inverse Laplace transform of U of S, right? Now, you remember, anytime you see an S in the Laplace domain, that's a time derivative in the time domain, right? So this S cubed, this is really like 3 time derivatives. So really, the inverse Laplace transform of S cubed YC, it's just YC triple dot, right? So this term becomes YC dot 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 of time, right? So we go from the S domain back to the time domain, right? Okay, then plus A2, same thing, S squared, this becomes YC double dot of t plus A1 YC single dot of t plus A0 Y of t, right, is equal to U of t. Right? Okay, so now what we're going to want to do is let's go ahead and solve this for the highest order derivative, right? Because this at this point was just a linear ordinary differential equation. And again, I hate to keep showing you prerequisite videos, but we talked about this, about taking a linear ordinary differential equation and writing it in state space format over in this video over here. In fact, I will leave a link to the exact timestamp of that video of where you need to go in order to see where we derive this. But again, I'm going to assume that you're following along with the curriculum and you're happy with this idea. But again, all I want to do is let's just move everything. I'm going to solve for y triple dot because that's the highest order, right? So this is pretty easy. We end up with just what? Y triple dot c of t is equal to negative a2y double dot of c minus a1y single dot c of t minus a0y of t plus u of t, right? Okay, so there we go. Now we're in the position where we can write a state space representation of this third order linear ordinary differential equation. So I'm going to define a state vector x as just being three states, x1, x2, and x3, right? And what I want these three states to be, the first state is going to be yc of t, the second state is going to be yc dot of t, and the third state is going to be y double dot c of t, like this, right? Okay, so now at this point what we can do is we can basically just write our state space representation. Okay, so let me erase this. I'm going to keep the diagram up here. We're going to leverage that in a second. So now if I take the derivative of the state vector, right, x dot of t, well, that's nothing more than take the derivative of everything, right? So that is y dot c of t, y double dot c of t, y triple dot c of t, right? Okay, and hey, look at this. We already have an expression for y triple dot. It's this entire thing. So go ahead and substitute that in for y triple dot. So we end up with, it's y dot, I'm going to drop the sub t notation so I don't have to keep writing it. Double dot, and then y triple dot was this thing down here, right? It's minus a2y double dot minus a1yc dot minus a0yc plus u, right? Okay, and now what we can do is we can write this in matrix form if we want. So let's pull out it like this. So I'm going to pull out yc, yc dot, and yc double dot. This side, okay? So now we see this is going to be a what? It's going to be a 0, 1, 0, 0, 0, 1, and then we end up with what? Minus a0, minus a1, minus a2, right? And then I need to have a plus 0, 0, 1 u, right? Would everyone agree? Great, so if that's the case, let's just go ahead and call this matrix here your A matrix, call this matrix here your B matrix, and we basically have a state space representation of how to get YC. So we end up with x dot is equal to AX plus BU, right? And here's your A and here's your B matrix, right? Okay, so now what we can do is we can now write an output equation. So maybe, shucks, I didn't manage the whiteboard space very well. So let's come down here and see if we can cram this all in here. Let's go ahead and write what is the output of this entire system, right? If you look at this thing long enough, right, we can basically see that y, the total output, y, not yc, right? Earlier we were dealing with yc, but now I want the total output of the system y over here, right? Well, this isn't so bad, right? Because if you stare at this thing long enough, we see the total output, it's this signal plus this signal plus this signal. Well, what is this signal? This signal is nothing more than yc times b0. So I end up with b0 times yc of t, right? That's this signal right here. Now, I got to take care of this signal. What is this signal right here? It's b1 times SYC. Again, you got to remember, when you see an S in the Laplace domain, that is a time derivative in the time domain, right? So really, this signal right here, this is like YC dot, right? And similarly, you look down here, this is YC double dot, right? So you follow this diagram, you see this signal right here, this is nothing more than B1 times YC dot. This signal here is B2 times YC double dot, right? Okay, so we end up with this plus B1 YC dot plus B2 YC double dot, right? And again, you stare at this thing long enough, you say, hey, golly, I can write this in matrix form, right? I can write this as a B0, B1, B2 times YC dot, YC double dot, right? Heck, you can even say plus 0 times U, right? That doesn't do anything. So again, let's call this matrix your C matrix, call this your D matrix, right? Oh, and I guess we probably should have mentioned, I forgot to mention, right? But this vector right here, isn't this basically the state vector, right? Over here, right? Similarly, up top here, this is your state vector, so that's where we're getting our state equation. So here, we basically have y is equal to cx plus du. And I guess I should take off the bar on the u and make sure there's no bar on the y, because again, this is it came from a transfer function, right? So this is a single input, single output. So the input and output are scalars, not vectors, right? Whereas the state vector here is definitely a vector, right? So here you have it. This is one way to go about obtaining a state space representation, right? Because this is what we were gunning for, right? This is basically a state space representation, right, of the transfer function here. So you now have the A matrix. The A matrix has this interesting form, right? The A matrix has ones on the super diagonal, and then the coefficients of the characteristic equation show up in the bottom row in sort of reverse order with a negative sign in front, right? You can see that here. The B matrix is really easy. The B matrix, it's all zeros except for the very last row has a 1. And then the C matrix is interesting because the C matrix has the coefficients of the numerator polynomial of the original transfer function, right, in this order, but with no minuses, right? Okay, so this representation where again you have the ones on the super diagonal, the coefficients down here, and the coefficients here, this is referred to as controllable canonical form. Gosh, I really ran out of board space. I'll just write it here in the middle. So it's controllable canonical form. Okay, and before we get too far ahead of ourselves, maybe what we should do is let's run over to Mathematica and double check that this A, B, C, and D matrix actually do indeed yield the original transfer function that we were playing with. All right, so here we are in Mathematica, and all we need to do is we want to check if the controllable canonical form state space representation that we just developed, does it actually result in this transfer function, right? This is the one we were working with. So the first thing we're going to do is let's go ahead and just get our A, B, and C matrices of the controllable canonical form into Mathematica. And again, I've just kind of prepared this off screen so you don't have to watch me type all these matrices in. But again, here's our A matrix with the 1 on the super diagonals and the coefficients of the denominator sort of in reverse order with a negative sign. The B matrix is 0, 0, 1. The C matrix is the coefficients of the numerator in kind of normal order with a plus sign. Okay, so now what we need to do is let's use the formula that we derived in our state space to transfer function lecture, right? That was just, what was that? It was, let me just write it out. Recall that we have G of S is equal to C S I minus A inverse B plus D, right? That was the what we developed earlier. Okay, so let's do that. CMAT times the quantity inverse S times identity matrix of size 3 minus the A matrix dotted with the B matrix plus the D matrix. All right, I think that's what we should end up with. So let's go ahead and do that. Okay, we see, since these are all matrices, by the time you do all of the matrix multiplication, we end up with a 1 by 1 matrix. So tell you what, let's go ahead and pull out the 1, 1 element, just so I'm not, so I'm dealing with the actual value, not the matrix. And then maybe let's hit this with a simplify. Okay. Okay, so there we have it. That doesn't quite look the way we want it to, so tell you what, I'm going to assign this to a temporary variable, and let's go ahead and take the numerator and of that thing, and maybe let's expand it, okay? And let's do the same thing for the denominator. Okay, we'll expand that, and then wow, look at that. That looks exactly correct, right? So here's the numerator, and that matches. Gee, I wish I could put all this on one screen. Let me do this. Let me group a couple of these cells here and smash these down so we can see everything on one page. Okay, here we go. Numerator. That matches with this numerator. That's perfect. Here's the denominator we end up with, and that matches with this denominator exactly. So yes, we do see that this state space representation exactly corresponds to this transfer function. So I think we showed that this controllable canonical form, yeah, it works. All right, and the last thing we want to do with this controllable canonical form is I would like to reconsider that DC motor example we were discussing in the previous state space to transfer function video. So to avoid having to go back to the board and write this on the whiteboard, I thought we would just talk about it here in Mathematica. So again, if you remember in our previous video, we derived that this was the transfer function between the armature voltage of the motor and the velocity of the motor, right? It was this effectively second order transfer function. Now, what I want to do is I just want to rewrite this in a slightly different format. So what I'm going to do here is I want to get the coefficient of the s squared, or the highest order s in the denominator, to be a 1. So I'm going to pull out this term of Jm over La from the denominator, and then I'm also going to just move it into the numerator, as you see right here. So basically what this allows us to do is we've manipulated the transfer function into the format that we had looked at earlier, where we basically have a numerator polynomial over a denominator polynomial, but this denominator polynomial, again, the highest power of s has a coefficient of 1. So basically this is exactly the format we were just looking at when we were discussing this controllable canonical form of this transfer function. So in this case, right, here are the coefficients of the numerator, the b0 and the b1, and the coefficients of the denominator, the a0 and a1. So let's just do the exact same thing we did earlier, except now instead of having a third order state space representation, since this is only a second order transfer function, we expect a second order, or a 2 by 2 A matrix. So that's what we've got down here. So this is now the controllable canonical form state space representation of the transfer function, right? Now, the thing I would like to mention here, this is a somewhat abusive notation. In our previous lecture, we were using the state vector x to denote, if you remember, maybe I'll just write this down here. So recall in the previous video, we defined the state vector x as, I think it was, x of t was, what do we call it? I think it was the position of the motor, the velocity of the motor, and the current running through the motor, right? Something like this. Now, what's interesting about this is this x is not the same thing as this x. Maybe what we should have called this is like z or something like that. Because what I'm trying to get at and make sure that we all understand is that the state vector that you have with this controllable canonical form is not necessarily the same state vector that you started out with this when we started this entire process, right? In fact, for the discussion in this video, we're only talking about starting from a transfer function, right? You don't know what the state of this what the states corresponding to this transfer function are. In fact, the physical representation of these states change depending on what state space representation you use. So in this case, we're using this controllable canonical format, and I really can't tell you what does this state vector z really mean. There's no guarantee that the first state is the same thing as this first state, right? In fact, they're probably not. However, that being said, even though the states are different, the input-output relationship is still going to be the same. Okay, so yeah, enough of that sidebar. Let me maybe delete this. Let me change these back to x's. Okay, just so we're consistent with sort of the lecture notes. And now what I would like to do is tell you what. Let's jump over to Matlab and implement this particular controllable canonical form state space realization of the system and simulate it and just make sure that it stacks up with all the other representations that we developed in the previous video. All right, so here we are in Matlab, and I've pulled up this, if you remember, this is the exact same script that we ran in our last video, again, when we were talking about going from a state space representation to a transfer function representation. So, tell you what, let me run this script. It's exactly the same thing we talked about last time, and I think what we showed was that the original state space representation, right, we turned it into a transfer function using the C si minus A inverse B plus D, and we showed that these two are basically the exact same thing. thing, right? So I think if I run this, come on, compile, running. Okay, great, right? And you look at the scope, we saw that both of these are the exact same thing. So now what I'd like to do is we went from state space to a transfer function, and now let's go from the transfer function back to the state space representation using that controllable canonical format representation or realization, right? So to do that, let me just scroll to the bottom of the script. Let's just keep adding on to this. And in fact, again, I've prepared this off screen so that we don't need to watch me type all that in. So let me go here and I'll paste this in, and I'll say we'll go from transfer function to state space. Let me make a note here. How about using controllable canonical form? Whoops, I think I spelled that wrong. But anyway, who cares? You get the point, right? So here are all the coefficients that we just derived in the Mathematica discussion, and here are the A, B, and C, and D matrices in controllable canonical format. Again, I call them A tilde, B tilde, C tilde, and D tilde because I think further up on the script, yeah, we used A, B, C, and D to be the original state space representation, right? That was our original 3x3. And now, again, what's interesting is the original system was a 3x3, but now we've reduced it to a 2x2 system. Okay, so now what I would like to do is tell you what, let's go ahead and add on another state space representation down here. So I'm just going to copy and paste this one, and now this is the state space representation using controllable canonical form, right? So now what we need to do is we need to change this to A tilde, B tilde, C tilde, and D tilde, right? And now the input is the same input. It's just U1, right? Now it's only one input, right? Because this representation is a single input, single output representation, whereas the original state space had 2 inputs and 3 outputs, right? So in this case, I just want the first input, and I am now, tell you what, this is now, again, this is apparently Y1, it's theta dot again, right? Okay, so now what I'm going to do is let's just go ahead and add on a third port to this mux, and now let's compare all 3 of these, because again, all of these should have the exact same input-output relationship. So let me go ahead and run this script so we can define that A tilde, B tilde, C tilde, and D tilde matrices, and now if we run this model, running, and open up the scope. And again, look at that. They all land on top of each other. So again, I think we see that all 3 of these representations, if we're talking about just the transfer function or the input-output relationship between U1 and Y1, they're all the same thing.
All right, great. So that was the controllable canonical form. There's a lot of different other forms. There's the observable canonical form. There's input feed-forward canonical form. And actually, I'd like to take a look at another canonical form right now, which is known as modal canonical form. Now, this will hopefully make sense why it's called this in a second, but again, I think the easiest thing to do is let's again consider a transfer function. I like to look at concrete examples. Again, let's maybe do a second order to make our lives easier. So b2 s squared plus b1 s plus b0 all over s cubed, oh excuse me, no, third order, yeah, let's look at a third order, just like we did earlier, sorry, plus a2s squared plus a1s plus a0, okay? So again, this is our general form, and now, you know what, let's just pick some numbers for these a's and b's that's going to make our life a little bit easier and illustrate what we're looking at here. So let's call this, how about 2s squared plus 18s plus 40, okay, all over s cubed plus 2s squared minus 5s minus 6, okay? Now, for modal canonical form, what I'm going to do here that might make this a little bit easier and clearer of what we're doing is let's factor the denominator. So, in other words, what I mean is let's keep the top the way it is. The numerator should stay the same. But now, if you run over to Mathematica or any other, factoring or root finding, and you basically find the roots of this polynomial, we can write the denominator here as s plus 1, s minus 2, s plus 3. Okay, so we can clearly see where the poles of this system are at 1 at s is minus 1, positive 2, and minus 3. right? Okay, so now what I want to do is let's actually perform a partial fraction expansion / decomposition on this transfer function. And again, here's yet another video that you should have watched already over here, right? This is where we discussed how to do partial fraction expansion / decomposition on a complex polynomial. So let's do that. So if you do that, you can rewrite this as this, -4 all over s plus 1, right? We're going to isolate that, we're going to expand it to this first pole, and then let's expand to the second pole. So the second one, you end up with a 28/5 all over s minus 2, plus a 2/5 all over s plus 3, right? Okay, so at this point, what we can do is, you know what, we can visualize this system just like we did earlier in terms of, now these are like 3 individual, you can think of it, smaller transfer functions being all added together, right? So they all have an input. Remember, this whole thing was y of s over u of s, right? So their input u, output y. So again, let's just draw the diagram. So there's 3 of these smaller transfer functions. Let's start with the top one here. So this top one, I think everyone would agree, I can visualize that as like a gain here of -4 going into a little transfer function of 1 over s plus 1, right? So into this is u, right? Okay. And then let's do the second transfer function, the one over there. That is just a gain here of what? It's 28 over 5. Then that goes into a little transfer function of 1 over s minus 2. Right? Would everyone agree? This is also u. Okay? And then finally, the third one on the bottom, this is now a gain of 2/5 going into a little transfer function of 1 over s plus 3. Right? And again, this is still u coming in. Right? Okay, and now the output of this system, right? It's just the output of this plus this plus this. So all of these outputs, if I sum them up together on this far side, right? In, out of this comes y, right? So here you go. Here's a way to break up this transfer function, again, using a similar sort of signal flow diagram of in 3 fashions, like this, right? So if you look at this long enough, you can basically say, okay, let's write the differential equation that is associated with this first little one up top, right? And I think everyone is going to agree that, let me see, where can I, maybe let's see if I can jam it in over here. Let me erase this to get ourselves a little more board space. Okay, so this first one, right, this is nothing more than a first order differential equation of the form, let's call it maybe x dot 1, right, of t is equal to -1 x1 of t minus 4 u of t. Right? This second one down here, this is another, it's a separate first order differential equation, right? So now this is like an x2 dot of t is equal to, what do we have there? Positive 2 x of t, or x2 of t, right? Excuse me, plus 28/5 u of t, right? And finally, the third one is nothing more than x3 dot of t is equal to -3 x3 of t, right? Plus 2/5 u of t, right? And maybe as a quick sidebar, maybe let's just double check to make sure this actually works. So maybe I'll do this down here. We'll erase this in a second. Let's just say, you know, a side note. Let's just do our engineering check to make sure that this actually works. So in other words, I want to make sure that this differential equation corresponds to this sort of small transfer function up here, right? So in order to do that, let's just Laplace transform that top equation, right? So this is s x1 of s is equal to minus 1 times x1 of s, right, minus 4 u of s, right? Okay, so move this to the other side. So we have s x1 of s plus x1 of s is equal to -4 u of s, right? So now factor out the x. So we have s plus 1, and then x comes over on this side, is equal to minus 4 u of s. Okay, now let's solve for the output, which is the state here, or I guess this signal x1 of s over u of s, right? So if I just do that, you can clearly see this is minus 4 over s plus 1, right? So great. This here checks out with this here, which checks out with this here, right? So again, I think we got the differential equation correctly, and you can do the exact same thing for these two if you want. So yay, this all checks out. Okay, so great. Now, with this in mind, I think we're in a very good place, because now what we can do is, let's just write these three. This is a first order differential equation, first order differential equation, first order differential equation. Let's just write them all in vector slash matrix form. So in other words, let's stack all these up and call this, how about x bar dot, right? This is just going to be x1 dot, x2 dot, x3 dot, right, of t, right? Well, that's nothing more than these three equations, right? So that is, well, I'll tell you what, let me just do it like this. It's this equation, and then this equation, and then this equation. Just jam them in here, okay? And now, you look at this long enough and you say, okay, fine, let's write it in matrix form. So in other words, what I'm gonna do is I'm gonna pull out x1, x2, x3. Okay, so if you look at this, you're basically going to see we're going to end up with minus 1, 2, and minus 3 on the diagonals, right? So we end up with the poles on the diagonals of this matrix, right? And then I got to add the plus, I got to add all these puppies up, right? So now we've got the negative 4, 28 over 5, and 2 over 5. This times u of t, right? So what do we have here? If you look, we now have x dot is equal to some matrix. Let's call this thing the A matrix again, right? X plus some matrix, call this thing B times U. So here you go. Here is your state space representation of that transfer function. Well, hold on. I'm getting a little bit ahead of myself, right? This is a state space representation of these three differential equations, right? Now, what about the output, right? If you look at the output, we can now also write the output equation, right? The output equation is this plus this plus this, right? So we end up with y of t is equal to, what do we end up with? It's just x1 of t plus x2 of t plus x3 of t. Right? And again, if you stare at this thing long enough, you say, okay, let's write this in matrix form. So this is the same thing as writing 1, 1, 1 times x1, x2, x3, plus 0 times u, right? So we got y is equal to some matrix, call this your C matrix, x plus some matrix, let's call this d, u. Now, here's the A, B, C, and D matrix that corresponds to this transfer function, right? So here, this representation, you can see, again, with the poles on the diagonals, right? The poles show up on the diagonals, and now you can kind of see why this is called modal canonical form, right? Because the modes, or the poles of the system, show up on the diagonals, right? And again, this is something we've seen before when we did our diagonalization of an arbitrary A matrix using the eigenvectors of the system. You can get basically the poles or the modes to show up on the diagonal. So we got the modes on the diagonals. You get these kind of random kind of coefficients here. Your C matrix is all ones, right? And your D matrix is 0 again. So this is modal canonical form. Again, what we should probably do is we should probably go ahead and check that when I put this into C SI minus A inverse B plus D with this A, B, C, and D matrix, right? We recover the original transfer function. And again, I don't want to run over to Mathematica and break our flow, so I'll just flash up a screenshot showing me doing that in Mathematica. And yes, we do indeed recover this transfer function. So this is great, all right? This works out. Now, the last thing we should talk about then is again, we were focusing on this particular transfer function, but how does this work out in general? So in general, you know what, we could probably fit this right here in this small little space here, right? So in general, the way modal canonical format works here is if you have a transfer function, we should have prefaced this entire discussion here. This transfer function, we are going to make the assumption has distinct poles, right? And as we discussed at the beginning here, it is strictly proper. So it's a strictly proper transfer function with distinct poles. And again, if you watched our partial fraction expansion video, you understand why we have this assumption of distinct poles here. But again, if this transfer function fits these conditions, which, you know, 99% of them probably do, you can do a partial fraction expansion of this transfer function and make it look something like a constant k1 over the first pole plus a constant k2 over the second pole plus yada yada plus some other constant kn all over the nth pole, right? You can make it look like this. And if this is the way you do it, you can basically, via the modal canonical form, you can get a modal canonical form where the A matrix looks nothing more than these poles, well, I guess the negative p1s, right? Negative p1, negative p2, yada yada yada, all the way to negative pn. Right? And then zeros everywhere else. So you get a matrix which is completely diagonal, right? With these negative terms on the diagonal, and then you get a B matrix which is all of these k's, right? So it's k1, k2, all the way down to kn, like such, and your C matrix is ones, and your D matrix is 0. So great. So modal canonical form is actually very handy and very nice, right? So it's not too shabby, pretty easy to get to, right? So that's interesting. Now, if you think about this long enough, we've looked at now controllable canonical form, modal canonical form. How many others of them are there? All right, so to answer that question, I'd like to look at now other possible canonical forms using a similarity transformation. So again, remember in our previous video, we discussed similarity transformations. They allowed us to go from some state space representation of x dot is equal to ax plus bu, y is equal to cx plus du, and then what we could do is via the similarity transformation, we could basically turn this into another type of state space representation, right, which looks like z dot is equal to some a tilde z plus b tilde u, and y is equal to c tilde z plus d tilde u, right? So the idea with the similarity transformation, maybe I'll abbreviate this as st, right, is that we want to have a new set of states z. Okay, and the new set of states are related to the old or the original set of states x, right, via some non-singular square n by n transformation matrix T here, right? So again, here T, just to refresh your memory, right, this was a non-singular matrix, right? And if that was the case, right, in our similarity transformation video, we showed how you get A tilde, B tilde, C tilde, D tilde from A, B, C, D, and T, right? So that relationship was what? It was A tilde is equal to T A T inverse, right? B tilde was T B, right? C tilde was C T inverse, and D tilde was just D, right? That was the idea, okay? So now, what we should ask ourselves is, what is the transfer function representation of the original state space representation? And we already know how to do that, right? We said that this thing, maybe I'll do this in another color, has an equivalent g of s, right, is equal to c times the quantity si minus a inverse b plus d, right? Okay, how about this thing over here? This thing also has an equivalent transfer function of, maybe, I don't know if we want to call this like a g tilde, right, is c tilde si minus a tilde inverse b tilde plus d tilde. Right, would everyone agree? So, you know what? Let's work this thing out and see what we end up with. So, all right, how about this? G tilde of S is equal to C tilde Si minus A tilde inverse B tilde plus D tilde, okay? Now, let's just substitute in all of these expressions in over here, okay? So what do we end up with? We end up with C T inverse times S, now I'm going to write this here as that's just T times T inverse, right? Everyone agree that's the same thing as I? Okay, great. Minus A tilde, that was TA T inverse, right? Okay, this whole quantity gets inversed, and then B was, B tilde is nothing more than TB, and then plus D tilde was the same thing as D. Okay, great. Okay, we got that like that. Okay, let's do a little manipulation in here. Let's pull out, look at this, we can pull out the T on the left and the T inverse on the right. So in other words, let's write this out. So this is C T inverse, and now, okay, this is gonna get a little bit, okay, I'm gonna pull out the T over here, SI minus A, and then I'm gonna pull out the T inverse over here, and then I'm going to close this parenthesis so the whole thing is still inversed, right? So, okay, did everyone agree this is just a manipulation of what's inside the parentheses? Okay, great. Okay. Okay, now just to make our lives easier, let's make a couple of substitutions. I'm going to make another matrix M is just this quantity SI minus A. Okay, so in that case, we can write this thing as CT inverse TMT inverse TB, right? Okay, now again, let's go ahead and make one other substitution just to make our lives a little more simple. I'm gonna have another matrix, how about let's call it N as equal to M times T inverse, okay? So I just want to, right here, I'm just gonna make this a little bit easier on ourselves, so this is now T times N inverse TB plus D. Okay, great. Now I can just go ahead and look at this inverse, right? So if you recall the way inverses of products of matrices work, right? This thing is you just need to reverse the order and then individually inverse them. So in other words, this is N inverse T inverse. Right? Okay, great. Let's substitute that in for the inverse here. So we end up with C T inverse N inverse T inverse times T B plus D. Okay? Okay, now let's resubstitute in our expression for N, right? So this is CT inverse. Now I need to insert this. N, we said this was what? It's MT inverse, and I got to inverse the whole thing, right? TB plus D. Great. Okay, again, let's go ahead and use our identity here of if I have a product of two matrices that I want to inverse, you just have to flip the order and inverse each individual one. So this becomes T times M inverse. Would everyone agree? Okay, great. We're getting there. So this thing is C, T, T inverse. Now I got to flip these things. So this is now T, M inverse, T. Did I drop something? Hold on a second. No, I put that in. Oh, you know, I dropped this. Crud. See, this term, there should have been down here. I did drop this. There should have been a T inverse there. Sorry, everyone. Okay, yikes. So let me make sure this is correct. M. So this is T. Okay, this is the missing T inverse, right? There. T, B plus D. Okay, let me just triple check this now. C. T inverse T M inverse T inverse T B. Yeah, okay, good. This is correct, okay? Now, finally, let's substitute in what our M was. M was just that, right? SI minus A. Okay, so coming back up here, we have this whole thing again, which is now G tilde. This is what we're trying to calculate, right? So this is C T T inverse, now M inverse. So here we go. So M was SI minus A. Now I got to inverse this thing. And then here's the T inverse that I forgot, right? So this is T inverse T B plus D. Great. Now if you look at this, look, T inverse, right? This is just identity matrix. T inverse T, this is just the identity matrix. So we end up with C
times the quantity Si minus A inverse B plus D. This is what G tilde is. And you know what's crazy about this? Look at this and look at this, right? This is equal to the original G of S, right? So, what do we end up with this? We see that under a similarity transformation, right, the input-output relationship is maintained, right? I don't care what T you're using, as long as it's non-singular, it doesn't matter. You pick any similarity transformation, you will still get the exact same transfer function you started with, which again makes good physical sense if you think about what we're doing, because all we're doing is we're changing the definition of the states. We are not changing the behavior of this system, right? So the input-output behavior of this system, or in the original sense, or this transform thing, is the exact same. And if the input-output relationship is the exact same, that means the transfer function is the exact same, because that's what a transfer function captures, right? Is the input-output relationship of a dynamic system. So what this tells us now is, if you think about this long enough, is there are actually an infinite amount of state space realizations for a given transfer function. Let's just write that down, right? There are infinity number of state space representations for a given transfer function, because, right, there are an infinite number of non-singular matrices that you can choose from, right? It's just, it's kind of your pick, right? Whatever fits your application. So all of them will yield the same transfer function. So I don't think it's not fruitful for us to go and try to make an exhaustive list of all of the different canonical forms that you can use to represent a transfer function, because you will be sitting here until the end of time, right? All right, so I don't want to sit here, until the end of time, like we just said, but I do want to show you one tool in Matlab that will help us with this workflow. So again, let's come back to this script that we were adding to, and again, this is a thing we made when we were playing with going from state space to transfer function and backwards. So if we scroll up, if you remember in the previous video, we were using, where was it? Oh, right here. Right? We were using Matlab's state space to transfer function function to basically go in a direction from state space to transfer function. Well, you know what? Matlab has the opposite, right? So help TF to SS, right? Because that's what we're talking about today. And if you look at the documentation on this function, you see that, hey, this is exactly what we want to do. You give it a numerator and a denominator of a transfer function, and it gives you A, B, and C, and D of, well, I guess if you look at this, it shouldn't say the state space representation, right? It should say a state space representation, because as we just discussed, there are an infinite number of these representations. Furthermore, if you read this documentation, what's interesting is these A, B, and C, and D matrices are returned in what are called controller canonical form, not controllable canonical form, right? We just now calculated A, B, and C using controllable canonical form. So, you know what? Let's go ahead and do another method where we go from TF to SS. Now we're going to use Matlab's TF to SS, which is controller canonical form. Okay, so this should be pretty easy. We should just be able to call TF to SS, and we need to give it a numerator and a denominator. So I think the transfer function we were dealing with was, this thing. I think we called it GV alt, right? Yeah, that was the minimum realization of it. So again, maybe let me just F9 this. We'll see what it looks like. Yeah, here is our second order transfer function of the transfer function between the armature voltage and the velocity of the motor, right? This is what it was. So we already ripped off the numerator and the denominator right here using TF data. So this is exactly what I need to copy and pass into TF to SS, and what we should get out of this is an A, B, and a C, and a D matrix. Maybe what we should call this is, if you notice, we already used A tilde. A tilde is controllable canonical format. So you know what? Let's. I'm not terribly creative. Let's call it A tilde 2, B tilde 2, C tilde 2, and D tilde 2, right? So now these A, B, and C, and D are controller canonical form representations. So if I run this, you see, yep, we get some matrices, and we can look at the differences if you, just for giggles. Tell you what, let me clear this. Let's look at A tilde. So this was the A matrix for controllable canonical form. And now what Matlab just calculated for us was the A matrix for controller canonical form. And as you can see, they're not the same. They're kind of similar. But similarly, we can look at B tilde and B tilde 2. Right? Again, looks a little bit different. C tilde 2 looks a little bit different. The D's are going to look the same. They're going to be zeros, right? Okay, so now this is another representation. So again, just to check ourselves, what we should do is, let's come back to our Simulink model. Let's go ahead and get another transfer function. So, or no, sorry, excuse me, not a transfer function. We are going to get another state space representation, right? Let's get this here. This is now controller canonical form, and I will now change this to an A tilde 2, B tilde, 2, C tilde 2, and where's our D tilde? D tilde 2. And again, you now hook up the exact same input, and let's all compare again to make one big happy family of all of these outputs, which again should all be the same. Come on, the wires doesn't help, right? Yep, they're all theta dot. So again, you run this puppy, and we check the output of the scope, and again, every single one of these are the same. So as we see, every single one of these representations are all equivalent, at least from an input-output perspective. So, yeah, I hope this video was helpful. I hope you will also stick around, because now if you think about what we've done, we've talked about going from, in this video we talked about going from a transfer function to a state space. In the previous video we talked about going from a state space to a transfer function. In past videos we've also talked about going from ordinary differential equations to state space or to transfer function. So we now have a ton of tools to go about basically transferring between different representations of a dynamical system. So in our following video, we'll tie all of those together, and we'll show how to basically flip-flop between whichever representation you look at. So I hope you'll join us at that video. I promise it'll be fun. I promise there will be some references to Legend of Zelda. And yeah. So I think this is a good spot to leave it. I hope you enjoyed this discussion, and if so, I also hope you'll consider subscribing to the channel. Surprisingly, if you scroll down and click on that subscribe button, it really does help me continue to make these videos. And as we've discussed in the past, the new videos come out every Monday. So I hope I'll catch you at one of these, and we can all learn something new together. So until then, I think I'm going to sign off. Talk to you later. Bye.